Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The landscape of early 20th century physics was one of profound upheaval, a territory where the classical certainties of the 19th century gave way to the perplexing quantum realities. Within this charged intellectual environment, the phenomenon of radioactivity, discovered by Henry Becquerel, served as a primary catalyst for transformation. The emissions from radioactive substances, categorized as alpha, beta, and gamma rays, provided direct windows into the subatomic world, yet the view was often obscured and paradoxical. The nature of beta decay, the emission of an electron from an atomic nucleus, presented a particularly stubborn enigma. Early experiments using absorption techniques suggested a continuous spread of energies for these emitted beta particles, a finding that seemed to challenge the nascent principles of quantum mechanics, which favored discrete energy levels within the atom and its nucleus. It is within this crucible of debate that Lise, Meitner and Otto Hahn, working at the Kaiser Wilhelm Institute for Chemistry in Berlin, produced their 1921 paper, The Beta-ray Spectra of Uranium and Thorium. This work stands as a landmark of experimental ingenuity and interpretive ambition. This essay will undertake a profound and rigorous evaluation of the internal claims, methodological assertions, and conceptual frameworks presented within Meitner and Hahn's 1921 publication. It will proceed through a systematic analysis of the paper's core components, assessing the evidence and logic employed by its authors to construct their influential, though ultimately superseded, model of beta. Section 1. The methodological framework and the claim of unprecedented precision. Meitner and Hahn's investigation began with the establishment of a sophisticated experimental protocol, the foundation upon which all subsequent claims were built. Their chosen instrument was the magnetic spectrograph, a device designed by Otto von Baeyer, Otto Hahn, and Lise Meitner herself in earlier iterations. This apparatus employed a uniform magnetic field to deflect beta particles emitted from a radioactive source. The degree of deflection is a function of the particle's momentum, allowing particles of different energies to be spatially separated. These separated particles would then strike a photographic plate, creating distinct lines or bands. The authors presented their version of this technique as a significant refinement over previous efforts. They asserted an ability to achieve high resolution, meaning they could distinguish between beta particles with very similar energies. The core of their methodological claim resided in the meticulous preparation of their radioactive sources and the management of the experimental conditions. They utilized thin wires coated with radioactive material, ensuring a point-like or line-like source to minimize blaring on the photographic plate. The entire apparatus was housed in a highly evacuated chamber to prevent the beta particles from scattering off air molecules, an effect that would degrade the sharpness of the energy spectrum. In their writing, Meitner and Hahn articulated a clear confidence in the capacity of their method to reveal the true, primary nature of beta emission. Their argument for the validity of their results was therefore intrinsically tied to the asserted precision of their spectrograph. They presented the sharp, well-defined lines on their photographic plates as direct, mediated evidence of discrete beta energies. An evaluation of this claim reveals an exemplary piece of experimental physics for its time. The attention to detail in source preparation and vacuum technology was indeed at the forefront of the field. The resulting photographic plates, which they reproduced in their paper, do show remarkably clear lines. The internal logic of their methodology is sound, assuming the apparatus functioned as described. It would indeed be able to resolve separate groups of monoenergetic electrons. The unstated premise, which forms a point of later vulnerability, was the assumption that these photographically recorded lines represented the full and primary story of the beta decay process. Section 2. The empirical findings for uranium X1 and the postulate of discrete lines. The first major set of results presented in the paper concerned the beta spectrum of uranium X1, an isotope of protactinium. This substance was chosen for its strong beta activity and relative ease of isolation from uranium salts. Meitner and Hahn reported the observation of a series of sharp, distinct lines on the photographic plates exposed to uranium X1 emissions. They proceeded to calculate the energies corresponding to these lines with a high degree of numerical specificity. Their central empirical claim for this section was unequivocal. The primary beta radiation from uranium X1 consists of several groups of monoenergetic electrons. The paper lists these energy values, presenting them as fundamental constants of the decaying nucleus. The continuous background spectrum, which other researchers had observed, was acknowledged. However, Meitner and Hahn relegated it to a secondary phenomenon. Their argument, based on the visual evidence of their plates, was that the lines were the primary reality and the faint, continuous blackening of the plate was an artifact. They presented the clarity and reproducibility of the lines as proof of their primary nature. Evaluating this claim requires a close look at their data interpretation. The existence of the lines was undeniable. Their apparatus was clearly detecting groups of electrons with the same energy. The crucial interpretive leap was attributing these lines to the primary decay process itself. They were, in essence, arguing that the nucleus of uranium X1 expels electrons at a small number of fixed, characteristic velocities. This was a profoundly attractive idea from a quantum perspective, as it aligned the process of beta decay with the established phenomenon of alpha decay, where alpha particles are emitted with discrete energies, and with the emission of light from atoms, which occurs at discrete frequencies. The internal consistency of their argument was strong. Given the observation of sharp lines, the most direct explanation was that the source of those lines, the nucleus, operated on principles of discrete energy states. The claim was a bold declaration that the confusing continuous spectrum was a red herring, a complex secondary effect masking a fundamentally simple and quantum-like primary event. Section 3. The thorium decay series and the assertion of a general principle to bolster their hypothesis beyond the single case of uranium X1. Meitner and Hahn extended their investigation to the decay products of thorium. Specifically, they analysed the beta spectra of thorium-B, an isotope of lead, and thorium-C, an isotope of bismuth. Their declared purpose in this section was to demonstrate the generality of their findings. The paper presents a new set of data, another collection of photographic plates and calculated line energies, this time for the thorium series. They reported that these substances, too, exhibited sharp, discrete beta ray lines. The core claim of this part of the work was that the phenomenon of discrete primary beta emission was a universal feature of beta decay, common to different elements and decay chains. By showing the same qualitative effect in a completely different radioactive family, they transformed their initial observation into a candidate for a general law of nature. They argued that the presence of these line spectra in both the uranium and thorium series provided powerful evidence for their model. The evaluation of this section rests on the strength of this generalization. The experimental work appears equally meticulous. The lines from the thorium products were again sharp and measurable. The logic of their argument is one of scientific induction, having observed the same phenomenon in multiple, independent instances. They inferred a general principle. This was a standard and powerful method of scientific reasoning. The intellectual force of their paper was significantly amplified by the step. It moved their claim from a specific observation about a single isotope to a comprehensive theory about the nature of the beta decay process itself. The presentation of this corroborating evidence from the thorium series made their overall thesis substantially more compelling to the contemporary scientific community. It suggested that a fundamental secret of the nucleus had been unlocked, a secret that was written in a language of discrete energy lines, applicable across the periodic table of radioactive elements. The persuasive power of this section was immense, as it appeared to close the case on the fundamental character of beta emission. Section 4. The central interpretive hypothesis of primary and secondary electrons having established their empirical bedrock, the existence of discrete beta ray lines. Meitner and Hahn dedicated a significant portion of their paper to constructing a theoretical framework to explain it. This section contains the conceptual heart of their 1921 work. Their central hypothesis was a two-step model of beta decay. First, they claimed the nucleus emits a primary beta particle with a single, well-defined kinetic energy corresponding to one of the lines they measured. This primary electron then exits the atom. In its passage through the electron shells of its own parent atom, this primary beta particle could interact with and eject one of the orbital electrons. This ejected orbital electron was what they termed a secondary beta particle. They proposed that it was the secondary electrons, ejected from various shells with varying amounts of energy, that created the faint, continuous background spectrum seen on their plates and reported by other researchers. The core of their argument was a causal separation. The discrete lines originated in the nucleus, while the continuous spectrum originated in the atom's electron shells. This model was elegant and, for a time, deeply satisfying. It preserved the quantum-like nature of the nucleus by assigning it discrete energy transitions, while simultaneously providing a plausible physical mechanism for the perplexing continuous spectrum. Evaluating this claim reveals its ingenuity and its hidden flaws. The proposed mechanism of a primary particle ejecting a secondary one was physically plausible, analogous to the photoelectric effect where a photon ejects an electron. The model successfully reconciled the two seemingly contradictory experimental results lines and continued into a single, coherent narrative. A subtle intellectual maneuver here, an almost imperceptible piece of ironic foreshadowing, was their treatment of gamma rays. They argued that these discrete beta lines were the electron equivalent of gamma rays, suggesting the nucleus de-excites by emitting a particle. In some cases, they proposed, the nucleus might emit a gamma ray instead, which would then eject an electron from a shell via an internal conversion process. They saw these processes as related but distinct. The essential weakness of their model, invisible in 1971, was that it misidentified the cause and effect. The lines they observed were real, but they were the secondary effect, caused by gamma rays from the nucleus ejecting orbital electrons. The continuous spectrum was, in fact, the primary emission from the nucleus. Their beautiful, logical model had inverted the physical reality. Section 5. The proposed correlation between beta and gamma ray energies. In a final piece of analytical reasoning, Meitner and Hahn attempted to quantitatively cement their model by linking the energies of the beta ray lined to the energies of gamma rays emitted by the same substances. They hypothesized that the energy of a primary beta particle should be related to the energy difference between two nuclear states. Similarly, a gamma ray's energy corresponds to such a difference. Therefore, there should be a discernible relationship between the two types of emissions. They proceeded to compare their measured beta line energies with the known gamma ray energies for their chosen isotopes, particularly from the Thorium family. The claim they put forward was that such a correlation existed. They suggested that the energy of an emitted gamma ray was equal to the energy of a beta line plus the work required to remove that electron from a specific atomic shell. This was an attempt to create a unified energival scheme for the nucleus that could account for both types of radiation. The evaluation of this claim shows the authors pushing their framework to its logical conclusion. The search for such a correlation was a scientifically sound endeavor. A successful demonstration would have provided nearly unassailable proof for their model. However, the evidence they presented was suggestive rather than definitive. The numerical agreements they found were approximate and required some interpretive flexibility, while some beta energies seemed to correspond neatly with gamma energies minus a plausible electron binding energy. Other lines had no obvious gamma ray counterpart. The authors themselves presented this section with a degree of academic caution, acknowledging the complexities. Their claim of a correlation was more of a promising research direction than a fully established fact. This part of the paper highlights the immense difficulty of nuclear spectroscopy in this era. The available data for both beta and gamma energies had significant uncertainties, making definitive correlations challenging. This section, while intellectually ambitious, the least robust part of their argument, resting on numerical coincidences that are compelling but ultimately incomplete. Section 6, the intellectual reception and the unravelling of the central claim, the 1921 paper. Meitner and Hahn was received as a major achievement. It offered a clear, quantum-friendly solution to the beta decay puzzle, backed by what appeared to be impeccable experimental evidence. For several years, their model of discrete primary beta lines became the dominant paradigm. However, the work also spurred further investigation, particularly at the Cavendish Laboratory in Cambridge, led by Ernest Rutherford. The subsequent re-evaluation of Meitner and Hahn's central claim came primarily from the work of Charles Drummond Ellis. Ellis, initially a proponent of the Meitner-Hahn model, began to harbour doubts. He devised a new type of experiment using a calorimeter, an instrument designed to measure the total heat energy released by a radioactive sample. The logic was simple and powerful. If the primary decay process released electrons of discrete energies, as Meitner and Hahn claimed, then the total heat produced by a large number of decays should correspond to the average energy of these discrete lines. Ellis' calorimetric experiments, culminating in a definitive 1997 paper with William Wooster, yielded a startling result. The average heat energy per decay perfectly matched the average energy of the continuous spectrum. The energy of the discrete lines was entirely missing from the heat balance. This finding was a direct, fatal blow to the internal claims of the Meitner and Hahn paper. It demonstrated that the continuous spectrum carried away the actual decay energy, and therefore had to be the primary emission from the nucleus. The sharp lines, so beautifully measured by Meitner and Hahn, were a side effect. The true explanation, which Meitner herself would later help confirm, was a process called internal conversion, where a nucleus de-excites by emitting a gamma ray that, before leaving the atom, transfers its energy to an orbital electron, ejecting it with a discrete energy. Meitner and Hahn had masterfully measured the secondary effect. The great irony, a theme of some intellectual poignancy, is that their meticulous precision and powerful logic were deployed in the service of a fundamentally incorrect conclusion. Their work framed the problem so perfectly that it led directly to its refutation and, in doing so, created a new, deeper crisis in physics. How could a nucleus, a quantum system, emit electrons with a continuous range of energies? This very crisis would compel Wolfgang Pauli, a few years later, to postulate the existence of a new, unseen particle neutrino to account for the missing energy. Conclusion in final evaluation. The 1921 paper, The Beta Ray Spectra of Uranium and Thorium, by Lise Meitner and Otto Hahn occupies a complex and essential place in the history of science. As a work of experimental physics, it is a masterpiece of its era, a testament to the author's skill, precision, and dedication. The internal claims, proceeding from the high-resolution capacity of their spectrograph to the observation of discrete lines and their generalization across radioactive families, are constructed with formidable logical coherence. Their theoretical model, proposing a primary discrete emission and a secondary continuous spectrum, was an elegant and rational attempt to accommodate perplexing data within the ascendant quantum worldview. The work's ultimate legacy, however, is one of profound and productive error. The central claim of the paper was a grand misinterpretation of reality. They had inverted the roles of the primary and secondary phenomena. Yet, the significance of a scientific work is measured in multiple ways. The paper's contribution was its very clarity and force. By presenting such a compelling, evidence-based case for discrete primary beta energies, Meitner and Hahn sharpened the problem of beta decay to an unbearable point. Their precise measurements of the wrong phenomenon provided the definitive data that, when reinterpreted in light of later calorimetric experiments by Ellis, made the true, continuous nature of the primary spectrum undeniable. This confirmation of the continuous spectrum created the fundamental conservation energy crisis that necessitated the invention of the neutrino. The 1921 paper, therefore, serves as a powerful illustration of the scientific process, where even a flawed conclusion, if reached through rigorous and transparent investigation, can pave the way for a deeper and more accurate understanding of the natural world. It remains a monument to brilliant experimentalism and a crucial, indispensable step on the path toward the modern theory of weak nuclear interactions.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.